so this session is Introduction to Android Platform Development. So I've gone through and pulled a few things together based on our current practices and based on my experience. This is by no means a complete overview of everything in Android, but I have tried to cover the big bits. So at least you'll know where to look. All right, so I've actually removed one thing. If somebody has the agenda, they'll notice that the Android pieces topic has actually been removed. But other than that, things have, the topics generally line up with what has already been laid out. We have a general Android overview, so I'm going to try to demystify what Android is and tell you what it is not, in my opinion. I'm going to talk about Gerrit and Git and feature our current Gerrit work and our current Gits and talk about, and we'll go to the Gerrit website and take a look at things, and we can go to the Android Gerrit website and look there. I'll talk about porting Android to a new platform. So this is some of the work that the Android team and the landing teams have done, some lessons from that. I'll talk about HALs and hardware acceleration, which is Android's, which is really unique in Android about how this actually works and why Android made the choices that it made with the HALs and hardware acceleration layers. I'll talk about continuous integration, and I'll finish up with LAB integration. All right. So what is Android? So I've laid out kind of the highlights here. Android is a framework, it's an operating system. When you get right down to it, you've got the kernel, you've got some non-upstream kernel extensions, you've got a set of shared and static libraries, pretty much standard libraries. Standard from a functionality perspective, but not necessarily from these are the standard upstream libraries. You've got a set of hardware, you have a set of hardware abstraction layers that users and the Android framework actually relies on to represent the hardware. You have a JIT-capable VM. JIT came in just-in-time compilation, came in Dalvik in 2.2. There's a 5 to 10x speed up with that, and 2 to 5x speed up. At least that's the documented numbers. The marketing numbers in 2.2. On top of that VM, the Android Activity Framework, it manages Android activities, and we'll talk about activities and how they're different than applications. And then Android applications, which are written against the Android Activity Framework. So that's it. You know, as Deepak says, it's a distribution. I tend to disagree with I don't like the distribution word, because Android, to me, is always targeted at a particular device. So if you use device distribution, I can get behind that. What we're talking about here is we're talking about things that run on these guys. You know, they're off most of the time, they're in your pocket, they're very event-driven, they have no, there's really no linear, you don't really use your phone or tablet in a linear manner. You're not sitting there working on it for any length of time, typically. I mean, you post to Google+, you check your email, you click it off, and you put it in your pocket. That's what we're talking about here, and Android really nailed it. And that's why it's so popular, in my opinion. They really nailed that usage case. And the Android Activity Framework and the Android applications that are written on top of that framework really support that usage model. All right, so, I'm sorry?
You had to show the slide.
I had to, yeah. So this is the canonical general Android overview slide. And I hopefully it won't keep it up here too long. For those of you who haven't seen this slide, this is the parts of Android. You have the applications that are written against the application framework. You've got the libraries that the application framework calls into. Typically, they are demand loaded. Some of the libraries like Bionic, which is the Android CLib, are statically linked. And we'll talk a little bit about Bionic. The Android runtime, of course, sits in this little box. It also relies on some libraries, which is why it is where it is in the diagram. And then, of course, it sits on the Linux kernel. Android doesn't make a big deal out of the fact that it's on the Linux kernel. There's probably 3 or 4 lines in the entire documentation that it's running on the Linux kernel. So clearly, the Linux kernel is a component of Android, but what makes Android Android is here. It's the way that the activity manager is run. It's the core concept in Android about how you develop apps. That's Android. All right, so I'm going to go through each piece that I had.
Zach,
Yes?
this slide, the first slide, is that what AOSP is?
This slide?
Yeah, like, is that what I'm looking at when you say Android generally is plus plus plus? Is that OASP?
Yes, yes. And in fact, when we pull down, all of these components are released as part of the Android open source project. So yes, when you download 2.3.5 now, you get these components. So you can actually, and when we ship a platform, what we're actually shipping is a compiled version of all of this. You can change any part of this framework for your own usage. And so when device manufacturers get this, they see, oh, well, great, I have a fully integrated solution that has this great touch interface, it's all event-driven, and I have every single library I need, it's all been pre-integrated, I don't have to worry about anything, and I can write my app in Java and get my device out the door in 3 months instead of 2 years. So there's a real big economic benefit to using Android.
Zach, there's an IRC. Are the slides available somewhere?
They will be. Okay, so the Linux kernel. So this is my experience dealing and developing against the Android Linux kernel that is hosted on AOSP. So the Android kernel that is hosted on AOSP is generally targeted at whatever device is coming out next. So right now, they're working on the next Nexus S. They choose a kernel version, they work on that kernel version until that device ships. Then, on their next device, they upgrade the kernel, they reapply their Android patches, and they start the next development. It used to be that Android only had one device. It was a phone. Now, Android has 2 devices. They're doing a phone and a tablet. I can imagine that as we move on in the universe, that'll expand to 3 and 4 devices, and it'll probably eat Chrome OS, I can imagine. All right, so developed on a stable kernel. The kernel is generally not upgraded during distribution. This is not universally true. It happened with 38, so they moved to 38 mid-cycle for Nexus 1. Upstreaming is not done.
Sort of.
Ish. So why is upstreaming not done? Anybody can guess. But I tend to think about it in terms of community time versus product time. The Google engineers already work 24/7. So they've made the conscious decision to effectively concentrate on what they're doing. They concentrate on their products. Now, they are getting big enough that they are now, and John is helping, and various people are helping to actually upstream as their team gets larger, and they're able to and they have more experience doing it too.
And there's a number of good examples of them working with the community well, and so I don't.
Right. But I mean, in general, they're not sending all of their patches up to kernel.org for a particular device. And everything is distributed at android.git.kernel.org. Everything. The current tip, 3.2 kernel, is on android.git.kernel.org. All right, so what are the non-upstream kernel extensions? We have wake locks, we have processor memory, which is a physically contiguous memory and construct. We have ashmem, which is the Android shared memory, which is virtually contiguous, pretty much kmalloc. We've got device enablement, which of course is all the devices that are around. Alarms, which John's been working on with Google. Logging, and the Viking OOM out of memory resource manager, which is actually a fairly interesting piece of work. And I'll take it just a quick aside to talk about it. So when Android's running out of resources, it will indiscriminately kill the last processy thing that was effectively used, referenced, etc., based on the activity, the activity kind of idea, and it just literally just says you're done, bye. And the activity lifecycle actually supports this intrinsically, so that allows Android to actually run on devices that may not have enough RAM. That are really low-end devices and still have quite a good user experience, because they really know, like, it's in your pocket. It's really tuned for that usage model. So these kernels are kept on android.git.kernel.org. Google keeps a rebase to upstream kernel now at kernelcommon.git, and then they also keep per architecture trees that are off of common.git at some point, and these are the stabilization trees. So it contradicts a little bit of what I said, where Google will choose a kernel tree and then move on it. The common.git is essentially this place where that work is now going on kind of on a continuous basis. And the MSM tree, of course, for Qualcomm, OMAP for TI, the QEMU, Samsung, and Tegra. So. But if you look at this, for example, the MSM tree is 2 months out of date. So they haven't taken an MSM drop for a while. The OMAP tree is, completely up to date. So that's what they're working on. And you can, when you go to android.git.kernel.org, you can actually see. So, for example, you have this lovely column that says last changed, and you can get a pretty good idea of what's going on, because you can see things like, common.git was done 2 days ago. That was the last change that went in, pretty hot topic. OMAP, 2 days ago. Qualcomm, 3 months ago. Clearly not the tip Qualcomm kernel. So this is, and you can use this to drill down to see what particular branch is unique, or what particular branch is getting worked on. So you can see that Google is actively working on a 39 and a 3.0. And this is their tip. All their stuff is out on here. Okay. So since I'm going to jump between the browser, I'll just keep it in this nice window. Okay. A set of shared and static libraries. So, as I said in the earlier session, there's a set of standard libs that are shipped as part of the NDK. Those are the things that Google has said, these are standard on an NDK platform. There's also an enormous amount of other libs that enable various aspects, enable hardware, enable board-specific things, SoC-specific things, product-specific things. They're not part of the NDK, but they are part of the platform. So when you compile the platform, you're gonna get this set of libs. Most of the libs are licensed from an Apache source. It's a Qualcomm, or it's a Google Android policy. Google, or Android, has also implemented, re-implemented most of the standard utils. So there's an LS, there's an ins mod. Little short, very, very stripped down, does exactly what it needs to do, takes almost no options, and is basically there as a Linux abstraction layer for all intents and practical purposes. That's why I put things like BusyBox on. It's not the easiest thing to use. But there is one nice thing about it, is that you can look at a nice LS implementation that's on like 2 pages. And that's a fun thing, you know. There's a custom C library. It's a Bionic based on the BSD libc. One interesting thing is that librt and pthreads are actually part of the Bionic libc. They're not separate libs. Which I believe, as Barrow said, we didn't have time to verify, but that's actually part of the BSD libc. Okay. Set of hardware abstraction layers. So HALs abstract hardware. HALs are typically implemented in a shared lib, and as people use a piece of hardware, that shared lib is demand loaded at that point in time, and then sticks around using Google's custom loader. So these HALs are unique. They hide the fact that you might have hardware acceleration versus not, which is why you can have a frame buffer HAL that is only a software frame buffer, and the upper layers won't have any idea. This also makes it easier to port Android, because a lot of their work a lot of their graphics work works whether you have hardware acceleration or not. So you might not get great performance, but you're running Android. The HALs give the Android framework a common API to run from. So you're not talking about opening dev/dev/proc/whatever. This HAL is really, it's really, for all intents, a Linux abstraction layer, so that people can essentially program to a C++ standard lib and completely ignore the fact that there's a kernel underneath. All right, so there's a JIT-capable virtual memory, virtual machine called Dalvik. So the unique thing is that each application, and an application in this context is APK, which is a container of Android components. Each APK, when it installs as its own user, and it will typically use let me think about a way to say this. So it will typically run, it will at least have one Linux process, and it may have multiple Linux processes that are, and it will always have its own instance of the VM. That's what I want to say. So all of these APKs, all of these Android components are running in their own instances of their own virtual machines as their own user, and Android uses that to essentially protect one set of activities from another set of activities. And they'll use an RPC mechanism called binder to actually communicate between these two activities. And binder will run over the Android shared memory abstraction or the processor memory abstraction. And JIT has been in since the 2.2 Froyo. And then in 2.3, it got really nice concurrent garbage collection, And so that's why a lot of people are kind of sticking on 2.3 for a long time. Those two, JIT plus concurrent garbage collection, was the big performance increases and really made Android useful from a usability perspective. That was the thing that really busted the Android nut for users, because it was really a high quality experience after that. Okay, so Android activity frameworks. So activities are essentially to speak in terms of an OS terms, it's effectively a task and a message queue abstraction. So it actually is a message queue, and then there's a thing called a looper that reads from the message queue, and it actually executes the task activities. An activity may or may not have its own process. The process may actually span multiple activities may be in the same process, but it actually Android actually determines that at runtime. So again, we are further abstracting ourselves away from a traditional OS, right? I don't care how many processes I have, I'm just abstracting things into activities, and the activities go through an activity lifecycle. So an activity is essentially this looper plus a message queue, and there's an activity stack, and so as you interact with your Android device, things that you have recently, you've just brought up are launched and go onto the top of the stack, and that's what you're actually looking at. The thing that you were currently looking at then goes is now pushed down onto the stack, and the thing that you haven't looked at in a long time, Android says, well, you're probably not really interested in that thing anymore, so if I really need resources, I'll just kill it. And I'm able to do that because I have this fantastic activity lifecycle that manages the fact that before I kill it, essentially the activity gets a callback at various points in the onCreate and on kill cycle, and you're able to save off work that the user has done already, and those are all really known, easy to extend parts, and it's very explicit. Android says you will be killed under these circumstances, and you need to implement these callbacks in your application. Munir?
Yeah, do they support multitasking? I assume how they do that.
Well, so I'll get to that in 1 second. Okay, so Android applications. So I didn't actually say this, it was on the slide, but there is no main in an Android app, which is cool, actually, I think. There's no main. You don't need a main. All these things are these activities that are really, can't think of the word. Anyway, they're just independent activities that, as you interact with them, the list of activities is the application. So if you're in for example a browser, right? You're bringing up a browser. The browser is one activity. Then you go and you say, oh, I want to go look at. I want to go to eat, so I'm looking at my browser and I click, oh, I want to see where this restaurant is. It's going to bring up the map activity, so it will send an intent over. I haven't really talked to you about intents, but it sends basically a message to another activity. That activity picks it up, and then the map gets displayed. So all these things, this stream of events is essentially the application. You do see when you're looking at like games that come online, they're more in that traditional application, and you can really see that actually when you use them. So like play Angry Birds, for example. Angry Birds, it really does feel like an application. It has a longer startup time. It has when you move away from it, put it in a background, it has a longer suspend time, for example. So it's more in that main application, but a real lightweight activity is great because you can pop those back and forth very quickly, and that gives a good user experience. It also means that when I want to do an application, I don't really need to think about composing everything into a big executable that I wanted to do and figuring out which lib I need to pull and do all this other stuff. If I need to produce a map, I just send an event over to the map with some data, and the map activities, set of activities will handle that. So it's very revolutionary and novel in that aspect. Yes. Yeah, I got the block back. But thank you, I do appreciate it. Okay, so that's the extremely rough sketch of Android. So, also very important with Android. Android is a framework. It's an operating system. It's also a development methodology, in my opinion. And that development methodology is heavily influenced by repo, Gerrit, and Git. So these are the tools that people use to produce Android platforms. It's intrinsic to the development model. Doing Android development without Gerrit is like doing kernel development without LKML. It's something people do, but the majority of the universe is built, the majority of the Android universe is built to use Gerrit. So, from a source code perspective, Android, like the execution framework, where Android is nothing more than a per instance virtual machine that installs things per user, and there's shared memory, and there's shared libs, static libs. There's even executables, Java apps that run on it, and the kernel. Android's nothing more than that. Android source is, when you compose it, is nothing more than a set of gits and a set of commits. And those set of gits is stored in a manifest file. And that manifest file is managed by a tool called repo. And a repo is nothing more than a for each git in this manifest file. So that's what we're talking about here. Repo also has a dual identity, which is, it is the interface that you use to upload changes to a Gerrit. So the manifest file, in addition to including all of the gits, will include the target review site that you're going to push your change to. So Git, we have both a browsable Linaro Git site, and we have the browsable Android Git site. So here's our git.linaro.org Git web, and you can look through these at your leisure. And we also have Google's popping up in the back. Nope. Oh, I'm right here. So, yeah, we've already seen this. All right. So, repo, as I've said, it's a for each git in a manifest. The manifest is just a set as an XML formatted file that gives each git location. It gives where that git should be checked out to in the tree, and then either what commit, either explicitly or implicitly, depending on how that XML entry is formatted. And then, of course, it has a target for the review. An example of using repo, it's extremely easy to get a tree, to actually get the entire components of an Android distribution. You can get those in 2 commands. Repo init, name the manifest, name the branch, the manifest branch you want, and the particular file name. Typically what people will do is that they only will get repo init -u manifest repo, but because of the way we do builds, we actually typically use all 3. And then, so what that does is that checks out the manifest, which is also managed by Git, into a .repo file, and then when you run repo sync, it actually does that for each git command, and it's going to pull them all down. And that's it. There's no, where is this? I need this library, I need to go to this, this source control system, I need to, no. This is something that a device manufacturer is well within their means, right? Whether they can use Linux or not, this is simple. And what they're going to get is they're going to get everything in one integrated blob, and that's what they really can use to build a device. So, repo manifest stored in the .repo directory. We can take a look at one. Oh, come on. Or not. So, Android. This is our Android build site. This is where we do all of our Android builds, host our builds from. Take a look at, and Paul and James's infrastructure group were instrumental in getting this all going. So source manifest, this is what we're looking at here. So you can see a few components of these. It names the remote, so kernel korg, Linaro, OXBench, Egl community. We're actually looking at the LED snowball here. Then we have the path. So this is the path that it's going to check it out to in the actual Android source. The name is the name of the Git off of the remote Linaro here. So it's going to basically take that remote Linaro and cat on that, add a .git, and then check out revision Linaro Android 233. So a pinned manifest, and I won't go through a pinned manifest, you can see it on the same site, but a pinned manifest is nothing more than that what you saw there with the exact commit, the exact SHA that you're referencing in that Git. And using that methodology, you can actually reproduce exactly the build that you've got. Because of course the SHA is unique across the universe, so that's the build. All right, Garrett manages change reviews. The standard Garrett lifecycle is well documented in Life of a Patch, so please take a look at that, and we can chat about that a little bit more one-on-one if anybody's interested. So we now have our Garrett set up. Garrett set up at android.git.linaro.org. We have a how-to, which gives the exact commands you need to either push a patch using Git or push a patch using repo, and how to actually log into Garrett. And so we're hoping this week that we can actually make that transition. See, that worked. So anyway, here's the how-to. And here's our android.git.linaro.org. That's not bad. So here we are, and this is my dashboard, and I can show people this a little bit more. You have a change that went in. The nice thing about this, as opposed to the email, is you can add people to the review. Other people can actually see the review. So, if you weren't on LKML, and LKML again is a bad example because you can always search and it's all listed on a website anyway. You can always comment, But anyway, this at least takes you through the entire cycle through the web interface. It's got nice things like if you look at the side by side, you can comment. You can comment in line, and anyhow, cool tool. All right, so porting to a new platform. This is pretty standard. Kind of reminds me of the U-boot port. We have a pretty good platform with device Linaro Panda board that was gone through a lot of sweat and tears, and you can use that as a basis for another board port. There's a couple of things. So the kernel and the Android, the kernel hands off to Android through a standard init, and it's an init that Android wrote. The init that Android wrote has a nice little hack in it that calls another init that's based on the board name. So this board name has to be right in the kernel, or else things kind of go south. This board name this board name is parsed from let's see. Well, it's called, there's a function, get hardware name, I can't remember, I think it's proc hardware info that actually contains the string. So that's really the handoff there, and that's the per SoC handoff. That's how Android knows what it's running on. So you hook up the correct init, you fix errors and paths in the init as things boot up. So you just look through the paths. Oh, that's wrong. The path should really be this. You keep rebooting until the whole thing comes up. Typically, it actually comes up pretty easily. And what you'll typically run into is that if you're doing software frame buffer, that'll be broken. So you'll debug that. All right. For Linaro specific things, you'll need to modify Linaro image tools, update the boot line, create code to install the bootloader, and modify the board config for the partition offsets, and then create an Android build job. That's a Linaro particular thing. Here's a typical example of a Egl Add Config. So this fantastic error is an error that people see a lot, and this is essentially that the frame buffer didn't come up. And if the frame buffer doesn't come up, Android crashes repeatedly, over and over and over and over.
How do you get these logs?
Good question. This is an example of a logcat log. So what you can do is, as long as you have a serial port, you can get your D message over the serial port. There's a shell there, and you type logcat, and you can get the logcat log. Logcat also integrates with the SDK, and you can do all sorts of very fancy things like log filtering, and you can add your own log headers, and there's about a million things. And if you're into Android validation, you do all that on a daily basis. Because in essence, this is pretty much it in terms of, well, if you're a platform and you're giving a platform to someone, this is typically what you'll get as the crash log. So if you're an SDK developer, you'll have a nice debugger, which is GDB with a bunch of insight on top that allows people to forget GDB exists. But it does tend to actually work fairly well. Though I like regular old GDB. All right, so just quickly, we're almost done. HALs. So HALs are typically abstracted into an SO. The SO is loaded on demand as people want to use Bluetooth or want to talk to Wi-Fi. There's also the RIL, which was the kind of the first HAL, and really kind of set the tone for the how HALs worked. The radio interface layer, of course, came out of the mobile space, where you had this. You basically had a modem, and there's a proprietary interface there that was always changing. It changed across all the platforms, and so they wrote a RIL, and the RIL worked out really good. So they just extended that whole concept across the board. And that's something actually to keep in mind when you look at Android and look at some of the design choices, is that they wrote these HALs to compensate for the fact that they're trying to run on every single SoC in the universe. And so that was their design solution to, we need a common interface. And you know, it's fairly rational, right? You know, give you a set of SOs, write your apps to those, and then essentially write an OS abstraction layer, so that the OS that you're using can do whatever it needs to do. And I think there was even a plan really early on in Android to actually be able to switch the operating system out. So they were kind of planning on that. I don't know where that is. I don't even know if that's reality anymore. But that is also part of the history of development and colors some of the design choices that you see. All right, so kind of the last part is continuous integration, which we've talked about in the last session. And we've also talked about, so I'll cover it again for people that weren't here. So in continuous integration, the idea is that you take a patch, you review that patch, you create a test build, you apply the patch to the test build, test that build. If that build passes, the patch goes in, the build fails, the patch gets out, is rejected. That's it. The nice thing is you can do from a patch by patch basis, you can integrate a build in real time. You don't have a freeze, you don't have any lag in terms of builds that come out, and you know that when the build came out, it's already been regressed. So you can release that build because it's valid. Vicky?
Just a quick question on the
Sure.
testing. So are you testing actual functionality of it, or are you just testing that it builds and doesn't create any errors?
No, you're actually testing functionality. You actually take the build, program it onto the board. Typically people will have, most of the SoC vendors will have these giant arrays of boards. You'll take it, compile it for that particular board, and then automatically place it on that board, run a regression. So of course your builds are only as good as your regression, but it actually turns out that that's pretty good. From an Android validation perspective, most mobile phone manufacturers validate using the monkey principle. There's a tool that does the 2-year-old test. So if your 2-year-old grabs your phone and starts messing with it, sending random events in, things like that, the mobile phone manufacturer will actually run monkey, and once they get to a 24-hour monkey run, they'll say, "Yep, good build, let's go." And that's a real metric in the phone manufacturer's release process. So, and I mean it does you know, pseudo-random vector automatic vector generation is a fairly standard way of testing even chips because of the complexities involved. So there's also monkey extensions for you can actually control monkey. You can actually send particular events and do targeting and fancy things. So,
Zach,
yes.
Do you serialize the merging and testing of each patch at a time? Because otherwise, potentially there could be a race condition where each patch works in isolation, but when combined, they cause a problem.
Yes, you serialize it in a perfect world. In a non-perfect world where builds have to go out, what you tend to do is you'll take a set of patches, and there'll be 8 or 16. You apply that patch set. Now, if any of the patches in that patch set cause a failure, the entire patch set is rejected. That improves throughput.
We're talking about very low amount of code. It also low
But it's not. But the key is that the patches are orthogonal to one another. So the idea is that they're, if one fails, it's because of that patch, and you're just binning them because you don't have infinite hardware. You want to ship a build eventually. All right. So then the last thing is LEB integration. So again, this is part of the Linaro integration. So LEBs are actually extremely easy to create. The Android build system is extremely easy to deal with. You create a manifest, you check it into the right branch. You configure Android build variables, which if you're interested, you can see on the build page. You kick the build off, and an hour later you come back and test it out with Linaro image tools. It's very simple, it's very easy, it's very fast, and it's improving all the time. So things like re-kicking off builds, things like logging into a build server to make a change. Those are all things that we've kind of talked about, and may or may not do. But the core functionality of just kicking off a build and letting it clack through and then testing that result is pretty solid. Typically, the only failures you'll get are if our remote Git repo is down. Then you'll get a failure in a build and you'll look at it and go, oh, the remote repo is down. Then you'll just have to work with that remote repo to fix it up. Now we're actually mirroring, so that shouldn't be such a big deal. Again, thanks to the infrastructure team for sorting that out. Then what we do, to be extra super safe, is we take the pinned manifest, we check that into a release branch. So again, that is every single, what got built, the release manifest is created, which lists the exact commits. We check that exact thing into a release branch. We do that build again. We retest it. That build should obviously work. And then that's the thing that we actually release. So actually all of our builds are double tested, in essence. But this is a useful metric. And you can actually see on that release branch the difference between the things that actually changed, because you can actually see the diffs of the commit, of the particular commit IDs. And then if you're curious, you can actually go and get those trees and actually look at the difference between the commit IDs. And then what we do on our manifest branch now, or on our release branch now, is as part of the commit text, I actually summarize what has changed in between those two commits. So you don't have to go and look at it, unless you're real interested or trying to bisect a problem. So, just 1 second for questions. Like everything, there's a wealth of information online, including eLinux. And that's it. So, thank you very much. And if anybody has any questions, then I'm here for the duration. So, or if people want to go get on the go-kart, then that's cool too. So anyway, thank you very much.